Elham, can I ask you to just share your screen? Okay, so welcome everyone to this week's Quantum Science Seminar. It's actually already number 55 of the Quantum Science Seminar. And we are very happy to have today Elham Kashefi speaking about verification of quantum computing. And since Andrew knows Elham much better than myself, he will introduce Elham now. And with that, start the seminar. Andrew, it's yours.
So thank you very much, Christian. So yeah, it's a pleasure to introduce Elham Kashefi as our speaker today and welcome her to the Quantum Science Seminar. Elham is a professor of quantum computing in the School of Informatics at the University of Edinburgh and also a CNRS Director of Research at Sorbonne University in Paris. Elham is originally from Iran, where she studied in Tehran before moving to the UK and completing a PhD at Imperial College. And then she went on to be a research associate at Oxford and MIT before taking up initially her position in Edinburgh and later at the Sorbonne University. Elham is well known as a pioneer in the area of verification of quantum computing, which we're looking forward to having her introduce to us and talk about the developments there in her talk today. She's also a pioneer in the area of quantum cloud computing. And interestingly, in addition to her academic research, combines these two topics in her work with the startup company that she co-founded, VeriCloud. So Elham, again, welcome to the Quantum Science Seminar. It's wonderful to have you with us, and we're really looking forward to your talk.
Thank you very much for this nice, kind introduction. It's a great pleasure to be here. Indeed, I would like to tell you something about the quantum verification. My goal is to introduce the field and hopefully once putting a bit of content, also making sure that we see a little bit of the latest development. Okay, so let me start first saying that what is quantum verification? And in fact, what is the problem that quantum verification is trying to solve? So the way that I put it, that we all have a quantum drama, is especially right now, this quantum drama is very well clear, is that we are getting these more and more powerful quantum devices. I don't put the picture of all of them, but indeed these devices are going to go beyond classical simulatability. And on the other hand, if you like, the task of verifier, us with the restricted computational task, we want to make sure that whether these quantum devices are doing what they are supposed to do. And this is really a quantum drama because, of course, everybody has heard that, like, have the supremacy has achieved or not? Do we have a certifiability? Have we really reached, classical simulity, etc., or not? But so that's a kind of a concept that you heard a lot about it already from other speakers like Scott Aronson ahead of the time. But you can even go ahead and see that when we have been looking at all the use cases that we have quantum chemistry simulation, which is supposed to help us with drug discovery. We want to find a new material, or we want to really solve optimization problem. And if they are done on these devices which are noisy, how do we know that this result is really correct? How do we know that this noise has not kicked out? Of course, we don't have yet fault tolerant quantum computing. So that's what I'm calling quantum drama. And that is exactly the focus of the whole entire field of quantum verification to address this question. So in a sense, to put the setup, so we are in the setting of, we have a classical, i.e. essentially we don't want to build another quantum computer to test another quantum computer, to certify another quantum computer. Or you might be working at NPL, National Physical Laboratory, who wants to put the certification on devices, or you might want to make sure that, should I pay to Amazon because it's really run the computation that I asked correctly to me? And in many, many scenarios, you are essentially a limited computational verifier, a user, the client, terrorist, and then you have this powerful quantum server, powerful quantum experimentalists, which are doing something, and the whole goal is to certify the correctness of the computation. Of course, why am I going to talk for 1 hour? Because every of these words need to be clarified. What do I mean certifying? What do I mean correctness? What do I mean what computation? But let's start slowly. So the plan of the talk that I have is a little bit telling you that, long time ago, almost 10 years ago, verification was established as a complexity question. It's a very, very interesting, exciting field. It came essentially from the question of like as a complexity question. And in order to address that question, we define this notion of interactive proof system, which is itself, again, another very old toolkit from classical computer science. So this is just to help us to very precisely formalizing what do I mean by correctness of computation in the setting of a verifier and prover. And of course, I'm assuming most of you are physicists, you don't necessarily care about this complexity question that makes us excited, but then I'm showing that actually this whole definition and this formal truth, why is it interesting and relevant? Because it's one way of saying that, okay, let me have this running example. Yeah, sure, we can trust that Google has done 20 qubit tomography. So as a result, if I do 100 qubit tomography, that's gone. That's done. This is exactly certifiable. But what we are offering with this interactive proof system is exactly formal way of knowing how we can give a correctness statement regarding a computation. So hopefully, really only at the end of my talk, if you're still with me, you will see that actually verification can be used as a toolkit for benchmarking and saying something correctly about the actual device and being more relevant. But let's start this journey. So let's go actually to the very beginning, which is the interactive proof system, one of the most exciting fields. I forgot to put the reference of the classical computer science, Goldbach et al., etc., who defined the field of interactive proof system and as a complexity question. So you see that, complexity classes defined in a many different ways, but, bear with me that we're going in this new way of defining it. So in this setting, essentially any problems, hardness of a problem, as I will give you example, can be looked at, okay, we have a protocol between a probabilistic polynomial time verifier V. So there is a party which is called verifier. I sometimes call it Ali, sometimes call it, client, which is limited. I see that's us. We can do some simple problem. We can multiply numbers. You can do calculation, which is done in the polynomial P. But then is have access and interacting with the computationally unrestricted prover P. Think of it, your interaction with your supervisor. You are the student, you are the verifier V, you have a limited knowledge and part of it, and then you're talking with your super duper supervisor who's have this access to extra knowledge thanks to its long lasting suffering in the science. So now the point is, in this interaction, you're sometimes able to decide the answer or figuring out the answer of the problem that seems to be very hard and you cannot doing it yourself by this interaction going. So this is exactly the setting of interactive proof system, while still you might see that why this is anything to do with for me to make sure that the Google supremacy has been achieved or not. You need to be, bear with me. I'm just setting up the stage. So now in this complexity in this interactive proof system approach, usually when you have a protocol, you can think of it, the verifier is the good guy, the prover is the bad guy, i.e. you never know the supervisor really know the answer to something, or is just making some random guess and telling to you or something, or just trying to convince you about some problem that is not actually correct or not. So you need to have some property for this protocol. You want to make sure if the answer, or what we call it, there is a language that you want to decide. For example, you want to know that if the numbers is prime, whether this number, you have the factoring, the factor of the number of the large number, or et cetera, can you evaluate the ground state of some Hamiltonian, etc. So you want to know that if it's indeed, there is a solution and this prover really knows the answer, after this interaction, the protocol accept. So you say, perfect, very good. I accept your reasoning and your interaction with me. On the other hand, the most important property, which we come back to it, is the soundness. So again, it's a terminology, but think of it like that if the prover is cheating, is really have no clue what is the answer, has no idea of how to prove it, it has a lot of deviation from what is need to be done, you want to make sure that no matter what that deviation or that cheating strategy is, the probability of accepting is is bounded by half. So this parameter, this formula, you might think it has nothing to do with physics, but just to bootstrap it all the way to the end, you will see that this element that no matter what the prover does It's exactly the strong assumption that I will later on show you, that no matter what the noise of your device is, I can say something about it. So these are very, very strong parameters that I'm not making any assumption, because I'm here no matter how this prover is behaving. But let's stick again to our mathematical definition. So there is this verifier, good guy, prover, bad guy. The protocol is interactively, they're going around, they're making a decision of accepting or rejecting, and these are the two properties, which we come back to them. Let's look at the example, why this interactive proof system actually is the right way to define complexity classes, like our beloved BPP, bounded polynomial problem that you can solve, i.e. the problem that you know how to do it. For example, if you want to decide a problem is prime, you don't need to talk to anybody. You don't need to talk to your supervisor. You can actually get the instance X, and by yourself, you satisfy, you're verifying that, yes, this number is exactly prime because there is an efficient algorithm to solve that problem. So that's exactly an interactive proof system, which would have no interaction with the prover. Now we go to a little bit more complex problem, like the NP problem that everybody knows, P is not equal NP, etc. Here is a good example that you need to get a little bit of advice from your supervisor. Like you want to factor a large number. You have no idea if this number can be factorized or not. But if your prover, if your supervisor give you the factors, then it's very easy for you to verify. You take those factors, which you don't know where they're coming from, because your prover has this ability to solve this problem, then you multiply, and you're able to really satisfy that indeed, if these are the correct factor, there is no way that this guy can cheat me, trick me. So far, so good. So this is a class NP. And this is the very interesting and surprising result. So exactly the same setting. Verify is only doing polynomial computation. The prover is just sending some advice. So now if you just allow this interaction to be not just one time, just one advice, maybe you send something to the provers, answer your question, you ask the next question, and you allow just a slight probability of cheating, but exponentially small. So compared to NP, we change just few parameters, a little bit of cheating possibility, and several of, still polynomial round of computation. This now suddenly cover the largest possible complexity class, which is calling polynomial space. So essentially, any computation that can be solved and decided in polynomial space is achieved with this interactive proof system. So why I'm still telling all of this thing, because the game is about to start. So we said, okay, P is inside the NP and there is the IP space. Why should you care? You should care because there is this very exciting result by Jane et al. Come in 2018 that is that for the first time, usually that we say, oh, we don't know what is the power of quantum versus classical. We show that in this large complexity class of P space, polynomial space, in fact, interactive proof system and quantum interactive proof system are exactly the same. What does it mean? It means that if you happen to have a super duper powerful quantum prover, which is trying to interact with some limited in power quantum verifier, and they want to interact, this result in 2008 showed that, well, in fact, there is no point to do quantum communication. There is no point to have quantum verifier. You can just put a classical verifier. And at this moment, you say that, oh, fantastic, because everything that I ever want to run on my quantum computer, like doing the factoring, doing quantum simulation, doing some sort of super duper complicated problem that I have no idea if the answer is correct or not, because it might be noisy, because I don't know the instant. Well, it seemed that this classical computer scientist solved the problem, because I will set up an interactive proof system. I just interact with my quantum device and everything goes well. So why I'm still talking here, why I'm still, 2008 till now, we still is like continuing for 20 years and there is the endless paper, all of my career has built on top of it. Usually if it was not on YouTube, I would have asked it to the audience to answer it, but I give the answer. The problem is that in this interactive proof system, if you were paying attention, I did not put any restriction on the prover. I said that the prover is unlimited, super powerful. You can come up with the answer using quantum gravity, can do whatever. Whereas the real question when you're talking about verification is actually the question that raised by Guttsman and then Vazirani and Scott Aronson promoted it strongly, is that indeed, the interactive proof system is the right language, is the right setting. We want to have a good guy, the verifier. We want to have this bad guy prover to be distinct, but we want this prover, this honest prover, to be himself is a bounded polynomial quantum computing. So what do I mean? If you don't follow all of this thing, is that essentially the interactive proof system as it's set up is not enough. because we want to also deal with the quantum computer. I don't want to verify a super duper mighty quantum prover, which is a virtual entity, if you like. I want to actually work with somebody who's building a quantum computer and then say that whether this quantum computer is acting correctly because it's really not noisy and is following the instruction, and hence I can certify the outcome, or actually this quantum computer is so noisy and part of it. So this tiny little of modification that, okay, I want an interactive proof system, but the prover should be BQP, it just turned out to be an open question. And in fact, it's still open question. So we have some answer. So we answer it in 2009. Yes, we can give you a BQP, which I'll show you exactly. There is a way of doing an interactive proof system and hence a verification, but your verifier is not classical. You need to give a little bit of the quantumness to this verifier, which is the single qubit random qubit. And then there was this amazing result a few years later that came by Reichard et al. That they said, well, again, you can have actually the classical verifiers, fantastic, everything goes, but well, you need to have two prover and they need to be entangled, and you need to make sure that they're not classically communicating, which is the rigidity of the Bell inequality that you might have heard. And yet another amazing breakthrough recently by Mahadav came out that said, well, okay, I can give you the classical verifier, I can give you the realistic BQP prover, but I need to make you to make some assumption that there is some problem, which is called learning with error, that we believe that quantum computer cannot break. So what I'm saying is that this very, very simple question, which is exactly going back to the core of the verification, can I, using my classical computer, test whether the result of this quantum computer is correct or not, i.e. think of tomography. Can I do like tomography, which I'm doing a bunch of measurement, is very efficient, whereas now I'm talking about 1000 qubit machine, which I cannot do tomography efficiently. So far, the answer is open. So I'm still inviting you all to work on it, although we claim part of that $25 from Scott, but I think if you really solve this problem and you go back, you will take the money back from us and it's handed over to you, the whole $25, because it's a very interesting question. Making no assumption whatsoever to answer this. And it's still from complexity point of view is very interesting. And it's from all the progress that we see in the field is also very interesting, because you might say that, well, surely right now people are building these devices and they are doing some sort of certification, they're doing some sort of benchmarking out of them. So what do you mean this open question? The answer is that this question is open because in all of those various protocols that you will see that it's popping out day and night about various aspects of verification, benchmarking, certification, there's always some underlying assumption. And that's very, very important. And maybe it is what it is. And maybe we can hope for making those assumptions more and more minimal and more realistic. But it's like, if one thing I want you to take home as a message is that be careful. Next time you read the verification paper, trying to understand exactly what are those underlying assumptions and which one of them making sense. I have an ongoing collaboration with Andrew. I'm learning a lot of things from him regarding quantum simulation. And it's exactly the type of question we want to do. What are those assumptions? Same with Valentine. Every time when we're talking about what are the assumptions that it makes sense in your setting that we can go. So that's the story. Okay, let's continue. So essentially, to wrap it up before actually telling you something concrete about at least one of these protocols, I want to give you a little bit more about the overview of the field. So indeed, so far, question of verification is being considered as interactive proof system. Let me remind you why this is the right framework to think, because I quickly show you the mathematical condition of this correctness and soundness. But now let's revisit it from the point of verifying a quantum computer. So if I have this protocol, this verification protocol, or this interactive proof system, the correctness priority, which was this formula that I wrote, it's guaranteed that if your device has no noise, if your device is really functioning the way that you think you're functioning, if your Hamiltonian that you're writing on pen and paper is exactly the Hamiltonian that your device has implemented, this protocol, the correctness probability means that, the protocol will accept. So the protocol will pop out a flag and say accept, and the outcome is correct because you are certifying that there has been no interference or some sort of limited noise or some sort of no deviation. So this is exactly the type of honest run that we want to have. I run a computation with a protocol, which is exactly a quantum computer. and I accept the outcome. But the most interesting that probably we spend the rest of my talk about is about soundness, because the soundness is exactly what we want to make sure that have I gone through the regime of noise or not, in the sense that we want to have this property that if the outcome, if the device is too noisy, it has been too deviation. It's like the prover is actually have no quantum computer even at hand. It's just basically a classical computer, which is sending me some random outcome. In all of those scenarios, we want to make sure that verifier rejects, except with the probability or exponentially small probability. And remember, this exponentially small probability except is exactly what I told you. The only reason that I have to put that except with the exponentially small probability is just because of this is the property of interactive proof system. And you can always say that this is acceptable because that's the confidence limit. So this is what verification in this setting means. And these are the type of protocol that people have been producing with various sort of condition and parameter. But these two core property should be somehow trying to convince you that, okay, it would be nice if I'm an experimentalist and I'm working in the lab, etc., to have a protocol which has these two properties. You know, if my device is going well, so perfect, good, everything is fine, take those outcomes, do the simulation, discover a drug or solve an optimization problem without being worried that they are okay or not. And whenever my device is saying reject, I should not be worried that this is oversensitive, because indeed, you know, it means that it's very, very highly that something has gone wrong. Okay, so where is the field going? You know, again, maybe just for the computer sciences among you, that there has been very, very different way of looking at this verification and defining this quantum interactive proof system. And they are a little bit like the QKD, that you have prepare and send QKD protocol, receive and measure QKD protocol, or device independent QKD protocol. And in fact, these are exactly the same sort of technique, but it's a bit updated to do not just QKD, you're doing it actually computation. So there are protocols which are called single prover prepare and send. So in this scenario, verifier, and again, it's important to know that there is various protocol, various scenario, because although at the end, finally, I give you a concrete protocol that hopefully is relevant, but what is happening at each time, when you're working with different platform, when you're working with different application, you need to see that which one matches your criteria, match your constraint. So these are a set of protocol that your verifier, or if you like, the trusted device, is a trusted device that prepares states, and then you don't make any trust assumption about what the server doing. So in that scenario, these are the parameters, these are the complexity, and we come back to this complexity because they are not necessarily very, very efficient, but that's the state of art. And we have written one of the reference paper that I put in the list of references, exactly these numbers and this overview coming from them. It's a bit outdated, but it's give you the way that people have approached to the prepare and send. And then there is another class of protocol, some of them are called certification or post-hoc verification or measuring only. That in the other hand, now here you're assuming the verifier has trusted measurement. So instead of having trusted prepare device, you have a trusted measurement. Now the server is running the computation or sending the qubit, but I have a single qubit trusted measurement. So this is yet another setting that it could be more suitable for some platform working with. And of course, there is this other setting that is device independent, in the sense that exactly you doing your verification based on the rigidity of CHSH or self-testing or etc. And it's this scenario. So you have entangled prover. You can think of it like entangled devices, but you're making sure that these devices are not classically communicating. And you see, as I said before, each one of them making some assumptions. So you need to see that which assumption makes more sense for the platform to go with. And here we go, and there is this complexity. So in order to make sure in the next remaining part of the time, I want to go through one concrete protocol, so you get a little bit of understanding of how we are actually doing it and how we are actually achieving it. Because maybe if you're not impressed yet, you should be impressed that actually we are able to verify without making any assumption on the deviation of the server. So again, it's very important to understand how does this no assumption scenario pop out at the end. So the protocol that I'm talking about is going to be the prepare and send verification. So it's an interactive proof system. I will interact with the quantum device classically and quantumly. I am a classical verifier. The only thing that I'm as a classical verifier will have is that I have a trusted random single qubit generator. So you can think of it like, to whichever quantum computer that is super powerful, I can test it. I can bootstrap my testing using only assuming trusted single qubit generator. So how does the protocol work? The protocol is that this verifier has some single random parameter nu, is interacting with this prover device, whatever you want. They send some qubit back and forth. They send some classical communication back and forth. At the end, you can define a density operator, which describes the joint state of whatever device has done, whatever this device has gone through the noise, and whatever randomness that the verifier has gone. And now finally, I can write a precise definition of verification, because at the end of the day, as you know, we theory people are just obsessed about definition. And once we get the definition, then you just hack the machine and you get the bound out of it. So what is the definition that I like to have? I want to be able to make such a strong statement that I have keep repeating, that I want to make sure if I'm interacting with the device, if I'm interacting with a quantum machine, if I'm interacting with the simulator, if I'm interacting with whatever device that is claiming to have doing a quantum operation, no matter what this prover's deviation, cheating strategy, noise model has, Markovian, non-Markovian, I'm entangling my device with something else, it's not actually quantum, I plug in a super duper high performance computing classical part of it. No matter what it is, I want to make sure the probability of verifier accepting an incorrect outcome to be bounded. Okay, so what does it mean, an incorrect outcome? How do I know that I have been fooled? We have been fooled if we are ending up to be in this subspace. This is the subspace of being incorrect, that, oh, my tag, my accept, reject is telling me, accept, everything is fine, go ahead, get the outcome, whereas the outcome is actually orthogonal to the ideal outcome. So let's say that I run some computation, I get some sample, or I get some quantum outcome. This quantum outcome in the scenario of no noise, no deviation, no maliciousness, it would have been the psi-ideal, but actually my outcome is orthogonal. So this subspace is a subspace that we do not want to be at it. So the property of my protocol should be this property, that on average, depending on the randomness that the verifier is chosen, the probability, the trace of my density operator ending up to be in this subspace to be bounded. And that epsilon, it would be exactly my confidence. So this definition is yet another way of writing the soundness definition that I was showing you before. So this is precisely, if I give you a protocol which has good enough correctness, indeed, in the sense that you give a device and everything goes through and it gives you accept. And meanwhile, I give you a guarantee that you will never get an accept is false positive. You're never going to get a false positive because of this bound that is I have proven for my protocol, we are done. And now, why should be you impressed? Okay, the definition, you write it down and you just calculate it. The point is, the point is that, you know, in this definition that I'm showing is supposed to be working no matter what that deviation is. I'm not even making an assumption this noise was IID, the noise is like I don't know, is a polarizing noise. No matter what it is, it should work. So how do we do that? You know, if you hopefully realizing that you don't believe me, I can do this. So the point is, we are using a method which is also very, very trivial method, as I always said, it's like almost like what you usually do. So you do several runs, some run that is computation, some run that is test run. Imagine this test run are the scenario that you know the answer. This is my old joke that my mom used to do that in my high school, that he will ask me a bunch of random questions that she already knew what's happened in the school about it, and meanwhile ask a bunch of other hard questions that she didn't know the answer for it, and then she could have made an estimate about, you know, how many correct answer I give for the test round to make sure that I'm lying or not lying. And I'm pretty sure all of us have been choosing this test, and this is precisely how you can test the quantum computer. So you run several times. Sometimes you're doing a computation that you have no clue what the outcome is. Sometimes you do a computation that you know precisely what the outcome is. And then there's one magical toolkit, which is called blind quantum computing or cloud encryption, whatever. Think of it some sort of crypto magic, you know, my wound that I'm putting there, such that the computer does not know, am I doing a testing or I'm doing a computing? So that's the main thing that you need to take it for granted, that I have a method to make sure that from the server point of view, you know, he has no idea, is it the computation run or test run, which is exactly randomization, etc., etc. And then I'm done. Then I'm done in the sense that I can show you the problem. So the method is what we call test or compute. You run some computation. This is a hard task. You have no clue if this quantum algorithm, the answer is correct or not. It's not like a factoring that if you give me the answer, I can multiply. Think of it as quantum simulation, finding a ground state of Hamiltonian, I don't know, solving some other problem in BQP. Quantum sampling, boson sampling, supremacy problem. None of this problem that we know their outcome, but interleaved it with a bunch of a test round. In this test round, you put something that you know very well the answer, because this is some solvable Hamiltonian. This is some sort of Clifford circuit that we know how to classically simulate. It's some sort of deterministic computation. And the whole theory of the proof technique that comes from this interactive proof system that I was telling you about, and all those techniques that is coming, is suddenly it allows us to, okay, just check the outcome of the test. If they are correct, you know that the prover has been telling you the truth. If they are not correct, reject because you know that part. So that's exactly the whole framework. So essentially, this omega, this beast that is acting on the device could be non-Markovian, could be any sort of deviation. I can entangle my device, could be actually not having quantum, not having entangled gate, etc. Because of my cryptography toolkit, it will be reduced, is a reduction technique, to a very, very simple test run. And then I just look at those test runs and it allows me to come up with an actual protocol. And another way to think of it, that this cryptography make the verification problem to become an error detection problem, and I completely bypass the complexity of the simulation. To give you a little bit of idea, trying to making all the way to the end of actually the punchline that I want to say. So let's take it for granted that there is some method that is this cryptography toolkit. I'm not going to open it unless later on you want to ask me a question, I can say that. But the idea is very simple. We create this random single qubit. They are like a QKD state. And plus theta is 0 plus e to the I theta 1. Andrew told me you know about quantum state, so this part should be very clear. So these are the random quantum state that the client or the verifier prepare. And remember, we said that we have a trusted single random qubit generator. These random qubits are sent to the server. Now the server should receive these rotated randomized qubit, make some computation on top of it, and thus computation is instructed by the classical interaction. And this is the way that you can show that essentially QKD for the encryption of your state and gate teleportation for doing the operation is allow you to do a completely something which called the universal blind quantum computing, that you run a computation on a device and the device has no clue what you have done, which is precisely the tool I showed you before. So now if I have this tool, just instead of just doing computation, I add a bunch of tests as well. So sometimes I'm doing computation, those red qubits are the one that, I have no clue what the answer to those qubits are because they are my general computation. And this orange qubit, in a second, I show you how it's created. They are isolated, non-interacting qubit that they are deterministically, I know the outcome, so those are the test run. So this is precisely test or compute. In the picture is that this is done in the measure-based quantum computing, but you can think of it in the circuit model or in the gate teleportation model. Essentially, I have a bunch of general quantum computation, some sort of graph state computation, I'm doing it. So within this, in a random position, I created an isolated qubit. How do I create this isolated qubit? Because if you look at this blue qubit, these are the qubit that the verifier sent to the prover. They are in the state 0, 1. And when the server is applying the control Z, all these edge in the graph state is a control Z interaction. Control Z interaction, if it acts on 0, 1, is actually not entangling it. So as a result, that red qubit plus theta minus theta is become non-interacting. It's become isolated qubit. It's a completely independent qubit there. Whereas if it was any other random qubit, they are interacting. So I'm creating this sort of test run in the various part of my computation. And here is exactly what I achieve I wanted. For this single isolated qubit, I know deterministically what should be the outcome. These are the questions that my mom will know the answer for it. So if I prepare a plus theta state, I'm asking the server to make a measurement in m theta, the answer deterministically is 0. And if I prepare in minus theta, the answer deterministic is 1. And you can think about the uncertainty principle, the QKD, etc. If you have just one copy of the state, you cannot guess what the state is to give me the deterministic outcome. So that's the core idea. I put a bunch of these tests run in between, and I run my computation, and I'm very happy because everything, the trap position and measurement, everything is hidden. The idea of a proof, just to show you, is that you can think of it like I have this beast that I'm asking some remote quantum cloud to implement for me. I just send every of those single qubit rotated. Then I'm telling them how to do this measurement and how this operation. And the important formula is just like the rest of our proof technique is that take the formula that I show you, that soundness and etc. So you write this joint density operator of whatever the client send, whatever prover send in this equation. If you go through it, or later on we can discuss, is that you see that we are consider the most general deviation that the server can do at each round. And the whole point of this magical crypto toolkit is that it allows me to decompose my general noise to the, in the Pauli basis. And we know that why dealing with a very global noise is complicated, because you have off diagonal. And what this blindness is doing is just killing the off diagonal, because I know that the server has no idea where the information is sitting, how the information is distributed. The main toolkit, I'm sorry if I'm rushing it through, but the main toolkit is a polytooling. So there is a very powerful toolkit that in fact is not the crypto toolkit, is exactly polytooling that allow me to do that. If you have insert enough randomization in your computation from the server's point of view, then essentially any coherent attack, any off diagonal can be reduced to just the diagonal element. So you can, in your calculation of the bound, you're getting rid of off diagonal, you're only left with the single qubit, which is the single test, you get a bound on top of it. So this toolkit of crypto is the toolkit of inserting polytooling, which is the tooling that maybe some of you are familiar with. Randomized benchmarking is exactly the tool that will tell you, coherent noise can be reduced to the local noise. And then I can get an estimate. And using this local estimate, I can say something about the global computation. We can come back to that. But again, so now I just want to spend the next 10 minutes of it saying, okay, it seems everything is done. Fantastic. We wrote this protocol, and for the last 10 years, I've been going around. So we have a very practical protocol with no assumption whatsoever. Why all of you experimentalists not running and implementing this protocol? I keep asking this forever. And the truth is that we were being a little bit lying, because in fact, we have been considering this question as a complexity question. We are computer scientists. We love writing our all classes and analyzing this thing. So this protocol were practical, but only from the verifier point of view. We have been so obsessed to make sure there is no maliciousness, there is no deviation, that we put almost a nightmare for the server. So now if you as an experimentalist wants to really pick up any of this protocol off the shelf and said, okay, I'm interested, let me implement. Well, the truth is that, it's not really the case that we can verify your computation of 100 qubit with 100 qubits. In short, for your 100 qubit verification, we needed another 10,000 qubit to do it. So it's a very recent work. We decided to be a little bit more honest, in the sense that trying to also make this protocol practical from server point of view. And there is even more problem. It's not just a matter of the overhead and the qubit count. You can say that, well, okay, we can wait for all these fault-tolerant devices to evolve, and then there is not much issue. But the point is that this verification protocol are also oversensitive. We are continuously reject to make sure that nothing wrong is accepted. But well, that's not very useful. If you continuously reject, we're not making any progress. So because we don't get any sample that is acceptable. So essentially, to wrap it up, is essentially all this protocol, including myself. So I'm claim criminal as well, that in the sense that we have been optimizing, we have been going through about this problem in the sense that, okay, you create this large graph of state. Out of this graph of state, you get a small little graph of state. And that's how we do verification protocol goes. And this is wasteful, given that how much hard time goes to creation of these things. We felt like we cannot just dump everything on the experimentalist. Well, okay, create for me this 100 qubit graph of state. I carve out of it a 20 qubit, and that's what I can verify. And in fact, there is even a beautiful paper by Haronov et al. That is talking about this. Making fault tolerance verification is a very, very challenging, and there are very subtle assumptions that you need to take. So it's not like, just make sure that the fault tolerant verification implemented. So finally, in order to make things, just to tell you exactly where is the issue, the point is that I show you this tester compute, and you can make your server computation very, very, very efficient, maybe with linear overhead. But where the nightmare comes from, because this is give you only inverse polynomial confidence. So you get this inverse polynomial confidence. And yet another magic tool that we always use is that, bootstrap via fault tolerance. So in the original paper that we write, and the paper that everybody has written, is that I give you a protocol of test and compute, which is inverse polynomial confidence. Then you do the fault tolerance on the server side. Well, this is problem of server and everything is fine. As a result, you have a huge server overhead. Essentially, all those protocols that I made you to go through it, they are beautiful results. They are very, very relevant. They are breakthrough in computer science, but they are not really practical. They are not really something that you can really pick them up and do. But of course, I'm telling you this thing because we have a practical protocol. Otherwise, I would not advertising all this problem. So the point is that we have a very recent result with my student at Lip6 and a colleague, Harold Olivier, also at INRIA, that we really revisited this issue. So, okay, let's be nice to the server as well, in the sense that if you have a problem which has classical input, classical output, which is most of interesting problem we want to do with quantum computer, like sampling, from the problem, like simulation, everything that we can do, then it is possible to come a protocol that I quickly show you later on that has zero overhead. Essentially, if you have a computer which is give you 100 qubit computation, you're doing 100 qubit computation, not even one extra qubit more, because the whole protocol is about repeating it. And it's no longer true. It was a folklore that we thought that we need to always put quantum fault tolerance in order to boost it. It turns out that I can actually put classical repetition code, and it allows me to boost and achieve exponential correctness and exponential verification already, and making this protocol server efficiency. I know that I only have 5 minutes left, but I want to tell you about all of these results just to tell you that now you really can pick this thing up and run it on the experimental setup. So what's the big deal? The big deal, as I said, is that we just changed the protocol. The protocol is exactly like before. You still need to send prepare and send. You still send the randomness. We just did a little bit of a better job of doing this test and compute. We really, it is no longer asking you to create a huge graph and I curve out of this graph a particular subgraph to do the computation. So it's a slight change. And in fact, this is something that we knew that it can be done, but we never sit down and write the security proof of it. The computation goes like this. You give me a computation, you have 5 qubit, I'm always going to work with 5 qubit, or you have 100 qubit, I'm going to always work on it. I insert this randomization as before, randomizing each one of them, then making sure that this trap is constructed exactly for the same target computation. So you're repeating, sometimes you're doing target computation, sometimes you're doing the test computation, but now this test computation is not curved out of your target computation. They are done in parallel. It doesn't matter how it is, exactly the same part of it. And now this is the protocol. So you run in your computation, you need to decide your security parameter. You have T many round that is test round, D many round that is computation. Your gray stuff is exactly the thing that you didn't know before. And your green and reds are the deterministic one. And all the good thing that is happening is also the analysis that I'm not showing. This is essentially the old protocol with new analysis, that now I can put some threshold. I can even say that I know that any correctly behaved devices up to 1% or 2% or 5% has some noise tolerance. So I put that threshold. I accept all of my test run up to this 5% threshold of the noise. And then I can tell that my computation is correct exactly exponentially up to this threshold, and I can reject the computation. So this is all of these things. So probably on the slide you can look at it. There is all of these various property of it, and there's this property that I went very quickly through over it. These are the property in order to make sure that this protocol is exactly can be done as a benchmarking. So the kind of the home-based message is that there is a lot of price to pay, and you need to be very careful about this thing. And yet another reference that I put is a recent paper that we wrote, because the community, what I was presenting in this talk was heavily what we call it verification that comes from the complexity theory. But there's a lot of work that's come from benchmarking and certification. And we try to make an umbrella of all of this protocol together. And you can see that in the general benchmarking, you want to make sure your device is correct up to whatever figure of merit that you want. You want to make sure that there is a minimal resources you're asking, and you want to reduce the assumption. And the protocol that I showed you is exactly doing that. In the sense, your figure of merit is the trace distance of your outcome. The resource is single qubit random, and the weakest assumption is quantum mechanics is correct. Or a bit more precisely, there's some noise independent. Again, I put it there if you want to discuss later on. But we are excited. We think that this thing is actually is more practical than anything we have done before. And we can see, of course, in the real practice, how practical the practicality is. Just want to finish the bunch of projects that we have that we are using it. So we have a project with Rigetti that we are actually trying to mimic this protocol for testing and do the noise construction. There is the Quantum Internet Alliance, which actually the photonic platform that they have is very much suited for this one. And this whole protocol comes from the fact that we wanted to implement, they told us we have only a few qubits, and we could not done what the original protocol. So it was a very nice project that comes out of the constraint defined by the experimentalists. Then there is also in the quantum simulation, we have a student with Pasquale that we want to see that if any of these things can go to the analog setting, these are the things that we're also working very closely with Andrew to trying to see this verification, is it suitable for quantum simulation? And of course, Quantum Computing Simulation Hub have a huge activity within the verification. And again, we have many platforms. So we are finally thinking we are achieving, after 20 years of doing theory, that maybe we can actually talk to the experimentalists and trying to understand what other constraint comes. So with that, I stop. Thank you very much for listening.
Yes, thank you, Elham, from my side and from all of us, actually. And yes, we have a bunch of questions for you.
Excellent.
We'll start with the first one. So this is the first one. Do you think there is a danger we try to apply more stringent verification criteria to quantum computers than we do to classical devices? If we do large-scale classical HPC calculation in science and engineering that are time-consuming and costly, how often do we properly address verification?
Very good questions, very interesting questions. So this actually, the field that you mentioned regarding HPC or even the cloud computing, this question exists. In the classical domain, you also have, if you look at the cloud computing, we are outsourcing a lot of our problem to be done on the, huge Amazon resources. And if the question of the verification was as hard of, I get all those data and I need to verify them again on my little classical computer, what was the whole point of it? So in fact, there are a lot of work, again, using of the classical crypto toolkit, addressing precisely the same question that you're saying, and is a new tool. Because if I'm working with a bit of let me put it this way, if I look at the normal hardware on my little laptop, why I don't do any verification on my laptop? Because of the fault tolerant threshold. Because the classical hardware has a really high fault tolerant threshold of the 50%. So most of the time can be guaranteed there is no noise that is going to destroy this thing, etc. So if my device is not attacked or it is not noisy, I don't need to be worried. So this is one way of saying it. So hence for quantum computer, we have to do it, whereas for classical computer, we don't need to do. And yet this is not correct. If you do a crypto analysis, there have been models that people have done what is called the strength test, that they needed to figure out actually the device working perfectly well or not. So the question of the verification is a field that exists in the classical computation, and particularly for the HPC that you say, and people are also coming with the technique. But in our case, I think in quantum is a little bit more complicated and we need to do more job because of the noise, because we don't have a way to get rid of the noise. Unless in future, even when the fault tolerance error correcting computation with 1 million qubit comes, you might still want to know that whether this answer is correct or not, because the point is for the quantum computer, we are going beyond the regime of simulatability. So, I mean, this is a sort of an answer, but you see, they are very much parallel between HPC and quantum, as you say.
Okay, thank you. So we go for the second question. So you have mentioned that you need in your verification protocol a trusted random qubit generator. How do you verify that you have a trusted random qubit generator?
Very good question. So indeed, this is exactly the type of assumption that I said that, like, when you start really digging into it, we're making some assumption. So the short answer is that I'm assuming it is a trusted single qubit measurement. So the best we can do, and that's why I said that this very interesting question is open. If I don't have classical verifier, it means that I need to make a little bit of a trust assumption or something. So the way that we are justifying it, especially think about the photonic quantum computing platform, because that's the best one that goes with this thing. I create a photonic quantum computer, it's sitting somewhere, and then I create in my lab a single qubit random generator, which you can do tomography. You can do as much of tomography on the single qubit to make sure it's a perfect device preparation, and then isolated it, put it in a black box, making sure that nobody touching it, use that one to send your single qubit. Of course, in the photonic, it's not too difficult to understand this separation. But now imagine I want to do in superconducting. Now I want to do this in the cold atom. I want to do all of part of it. And there are extra assumptions we need to make. That the bottom line, another way to answer your question is that these are assumptions we make, but assuming that, you know, my single qubit, instead of saying single qubit trusted measurement, I need to make sure the noise that exists in my device, that's what I'm writing, is independent on the randomness that I choose in the single qubit. And to me, this is a big assumption, but it's a much, much weaker assumption than saying, oh, my noise is IID, or I'm doing my computation over the 20 qubit and then everything should go. So the real game is that reducing the assumption, but you're right. I'm assuming it is what it is, and then I bootstrap it to the outside. And we have several other ideas of how to enforce that, how to build some sort of trusted execution environment, et cetera, but it's an assumption.
Okay, thank you. Then we have two questions that go together. So the first one is, how large should be the space of testing question that you know the answer compared to the full space of question you ask? And the second one is, if your test questions have to be something that's classical computable, then are you really testing all elements of the quantum computer? So for example, what do we really learn from a test run with Clifford circuits?
It's a very good question, all of this. You guys are good, you know, you're computer scientists. So let's put it this way. So the whole point, the whole game is that we are building a test run to be exactly the same space as a computation run. This is very, very important. So this is not the method that I do a test on the 20 qubit machine, and then I want to make a claim about the 100 qubit machine. No, I'm all the time interacting with the 100 qubit machine. I'm using the full capacity of your quantum device, but I tailor-made this 100 qubits. So if you look at it, when I'm saying test computation, is over the same 5 qubit that I'm doing my computation, but the interaction, if you like, the interaction is remain tensor product. So that's the easiest way. So I'm doing a 100 qubit machine. In the computation one, there is a whole wide range interaction that is make it classically unsimulatable. The server is thinking when I'm doing the test run is exactly the same way. It's turning on the same Hamiltonian. It's turning on the same circuit randomization. So from his point of view, I'm doing still the same 2 qubit gate and single qubit gate, but it makes them a tensor product. And because it makes them tensor product, the classical computation can be simulated. So back to the question of Clifford. In fact, our test run is not Clifford. The semantic of them are Clifford, but from the server point of view is always the full circuit computation. You're always running the 100 qubit. You're always running the same set of gate, but my randomization that has been de-randomized, it's making sure that in some scenario, these are the classically predictable outcome. In some case, they are not predictable. So that's, again, is a big difference with the randomized benchmarking, that you do something over Clifford, and you're hoping that this Clifford test also guarantee that what's happening to your non-Clifford test. We are not like that. We're doing the full set of operation.
Okay. Thank you. So then we have a question from the chat. Ranjit is asking, so it's telling many tests for your presentation. And then, do you have a list of criteria for verification of output intermediate results to check whether calculations are going wrong or not?
Okay, so this goes back to something that I was saying before, that is depending on the figure of merit. So when we say correct function, if you look at this, all of these zoo of the various protocol, people define figure of merit, and each different verification or testing or benchmarking has its own figure of merit. So for us, the figure of merit, which I show you, is a trace distance. So the only thing that we certifying at the end, and we say accept or reject, if you remember my soundness definition, is that your outcome with the high probability is not in this wrong subspace. So that means that the fidelity of your outcome is very, very, very close to the ideal one. So I'm giving only a correctness, a certification of the fidelity of your outcome. I'm not able to tell you anything about which gate goes wrong, what set of operation has been missing. Was it quantum or was it classical? At the current model, the way the protocol is done is a very, very, if you like, limited. It's just telling you the trace distance of outcome. We believe that if we dig into this test run, that, you know, when we see that what is rejected, what is accepted, it might be able to tell us something. In fact, in the project that we're doing with Rigetti, we're trying to do that. We don't want to just say, yes, accept or reject, because most of the time is reject, but we want to actually go back, say that, oh, it's reject because that qubit was noisy, etc. And that's much, much more difficult problem. So our criteria is just the correctness of outcome and fidelity of output.
Yes, actually, Ranit was asking a second question that goes in that direction, asking in case if calculations are going wrong, then you have list of debugging steps to identify and correct them.
Yeah, this is a very interesting question. As I said, we're trying to, as a little bit of doing a better job, because right now is exactly the sort of the usual thing. First, we wanted to give certification of outcome, but now we are trying to say that if it's really a benchmarking tool, not just accept or reject tool, then maybe the class of tests that I need to put among those gray one, it should be more diverse in a sense that from those reject, it should be to reconstruct the noise and be able to say that, okay, the noise was, I don't know, this single polarization noise, or etc. But this noise reconstruction is almost like there is a very beautiful set of result of this shadow tomography that is coming, that using very few measurement, you're able to, find the shadow of the general noise that you have gone through. So we're trying to add those methodology also to the picture, but currently we don't have them.
Then another question. So when you look more closely at verifying a particular device, to what extent can you reduce the cost of verification by making assumptions about things you think we know? And what danger might there be in making too many assumptions?
This is a very good question. Again, it's something that forever we wanted to say that, like, you want to say that if I make the noise tailor-made, so it's usually when we work with our collaborator, with this experimentalist, for example, the beauty of this thing, they know very well their model. They know exactly, I mean, okay, if you're talking about cold atom, they know exactly this is the dominating noise. If you're talking about NV platform, they know what is the dominating noise. So the short answer is that we still don't know how to use it. I believe that it must be the case in this toolkit. Instead of if I'm putting this omega, if I put the very particular noise model, it should work out. But somehow the toolkit, this reduction that we have, is so agnostic to it. We said that like it was whatever general CP map, I threw it and it become local map. So again, it's a type of question. We start working on it. We believe that this noise tailor-made should make this protocol more efficient, but we don't know how. Sorry.
Okay.
Invite me in 10 years' time. Hopefully I have something to say.
And then we have a last question. So regarding the testing questions, is there a way to choose the question in an optimal way in order to maximize certainty?
You guys are writing all the questions that I usually write, and I get a grant and another million to spend my next 5 years. Go ahead and write those grants. People give you lots of money. It's again is yet another very good question. I think I will reformalize it in the sense of, can I also formalize it to the particular application I want to have? Because so far I said I want to verify any general unitary computation. I didn't tell you, was this unitary circuit? Is it a sampling problem? Is it some sort of slightly better than quantum? Maybe is a Hamiltonian. So tailor-making to noise, tailor-making them to the particular application. These are exactly the two directions that we are hoping to go. Of course, you can say that to some extent we are doing this. When I was saying that if I'm picking this particular graph, this is towards that direction. Before the verification was that I could pick up a generic resource and now we are doing a verification and we were carving out of this thing part. Now we are one step ahead in the sense that if you know exactly which graph, which circuit you're trying to verify, I make sure my test run is exactly shadowing the same one. So if you give me a particular quantum circuit you have in mind, I don't construct random tests. I'm making my test exactly matching that. So this is a huge optimization, but maybe even more can be done on that domain.
Okay. So thank you very much from my side, Elham, and I leave the stage to Christian again.
Yeah, thank you also from my side, Elham. That was a great talk. It was a lot of fun listening and following it.
Thank you.
So what remains to be said from my side is to announce basically our fourth hot topic session that we have next week with 3 young scientists presenting their work. We have Paula Garcia Molina talking about variational quantum algorithm for eigenvalue problems of a class of Schrödinger type partial differential equations. We have Gadi Afek talking about precision searches for new physics using optically levitated sensors. And we have Qi Shu talking about quantum enhanced optical lattice clocks. And with this, I say goodbye for today and see you next week.